Damn, did you know that just over 14% of the world's generated electricity comes from hydropower? That's right, and here you can see that puts it just behind fossil fuels and then pretty well above all the rest of the renewable sources. So that's why today I wanted to talk to you about hydroelectricity and hydroelectric energy systems. My name is Sean. I'm a second year mechanical engineering major, and you might be wondering, why should I care? Well, as we all know, electricity is everywhere. It shows up in our homes, whether it be our computers or our appliances like our washers and dryers, our phones. It shows up in our cars and traffic lights. There's medical equipment, power tools, you name it. Electricity shows up just about anywhere where there's light or anything, any autonomous moving parts. It's all electricity, and so I think it's relevant. You might also be wondering, why me? Why am I delivering this speech? Well, as a mechanical engineering major, I may not have decided fully yet what I want to do with my degree, but something I've given strong consideration is energy resources, and more specifically renewable energy. I think it's particularly important for the future of the earth and humans in general. As of right now, as of the technological revolution, we use electricity a lot and we rely on it. It makes for better life. So if we want to continue doing this, we're going to need a way to continue doing it that's that we can do over and over again, because of course fossil fuels are, while effective, they are limited in supply, and also renewable energy helps protect the environment in terms of carbon footprint. So very important to me, very important to the earth, so I think it's important to talk about. With that, let's begin. I'll be giving an overview on hydroelectric dams, pump storage hydropower, and power electronics. Let's start with conventional hydroelectric dams. Of course, I'm sure we've all seen one, but if you haven't, you have a river, you block it off with a little wall, or maybe not so little. It builds up into a reservoir, and then you have an intake system and a channel leading down to a turbine attached to an electromagnetic generator. So it spins, the water pushes the turbine, spins the generator, it creates a magnetic field and thus current and electricity. It sends that up through wires and out into the grid to be used. And then of course the water is just dumped off and flows off, continuing on its path. This graphic comes from the Energy Information Administration, as well as the information behind it. Next, we have something very similar. Pump storage hydropower. It uses a lot of the same mechanisms, at least regarding energy generation. You start at a high reservoir up on, say, a hill or a mountain. It then flows down again, turns the turbine, turns the generator, and generates electricity that is then sent off to be used. And then the water, this time, instead of being dumped off into a river, is dumped off into a lower reservoir. Much like the upper reservoir, obviously, just lower elevation. And then that is then pumped up to be stored and then used for later. Typically how this works is water is pumped up during times of low energy demand and low wholesale price. And then once prices rise and energy demand rises with it, the water is then sent back down to be turned into usable electricity once again, and the cycle repeats. Of course, as you see here in the graphic, these are typically powered by other renewable energy sources such as wind and solar to make them as efficient as possible, considering it does take a little more to pump up than these systems generate. And according to a Polish case study on pumped hydropower storage, they account for roughly 90% of all generated or storage, energy storage around the globe, putting it far and beyond above second place lithium ion batteries. So definitely a big deal for holding on to our electricity, and it allows us to decide when we want to use it and how to use it most efficiently. Something that both of these systems have in common, besides their electricity generation properties, is the power electronics that they use. According to a review on power electronics and hydroelectric energy systems written by Raja Singh and his colleagues at the Indian Institute of Technology, these power electronics serve many purposes, and they serve to allow these hydroelectronic systems to function, and they also make them more efficient and effective thereafter. Some examples are grid integration. That means these electronics help operate the systems to get energy out into the grid so it can actually be used. Machine control, just general facility operations. It's what makes everything go around over there. Variable speed operation. So this is kind of the meat and potatoes for the pump storage hydropower. This is what determines whether you're in generating mode or pumping mode. And then voltage and frequency control. And this just all comes together to make these hydroelectronic systems smoother, they run better, and thus give us more usable and renewable energy. That's it. I hope I've done a good job to give a basic understanding of hydroelectronic power after covering hydroelectric dams, pump storage hydropower, and power electronics. Thank you.